Hi everybody, and welcome to the first video on the topic of kinematics, which of course, as you can see from the description here on my really nice bubble block lettering thing, is describing movement of an object. This is going to correlate with DLD number 4, which is going to be due either Tuesday or Wednesday this week. Now, something that I'm going to recommend to you guys on this is that as you're watching these videos, it might not be a bad idea to make a note or two on paper. You're going to be completing some activities on the physics classroom and some other websites, and it might be nice for you to have something in front of you that you can go back and reference and not have to switch back and forth and come back and watch this video again. So maybe you get a piece of paper out and write along, maybe not, it's up to you. So in this unit, I said before that we're going to try and describe movement of an object, and in physics there's really 4 ways of doing that. So we could go through and describe the motion of an object by graphing its position or its speed. We could describe it in words, say things like, oh, it sped up and then it turned around and then it came back. We could describe it using numbers and equations, and we can describe it by actually doing it. And so our goal is to be able to take any one of these 4 and to be able to turn it to the other 3. In other words, if I gave you a graph of an object's motion, I'd want you to be able to walk it out, I'd want you to be able to describe it in words, and I'd want you to be able to, solve some basic numerical things about it. If I said, hey, an object was moving at 3 meters per second, in other words, if I gave you the numbers behind it, I'd want you to be able to graph that, I'd want you to be able to tell me in words what it's physically doing. It's going forward, it's going backwards, speeding up, slowing down, and I'd want you to be able to walk it out. In other words, when we're all done with this, I want us to be able to go from any one of these descriptions to the other one, and we're going to have an activity for just about each of these 8 arrows that I just drew. That's more than 8, isn't it? Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12 arrows that I just drew right there. Before we get started, I think we all need to agree on some real basic vocabulary here, and I'm going to lie to you, but it's okay because I'm telling you when I lie. So here goes. The first one is the idea of position, sometimes known as location, and it's simple. It's where something is, and in physics we usually like to assume that there's this invisible coordinate system all over the place. So we'll say things like, oh, it's standing at, like the 4 meter mark, or it's, at negative 7 meters, or it's 7 meters behind the starting line, or something like that. It's simply a location or a position relative to some starting point. Of course, if everything was, always at the exact same position or location, that'd be pretty boring. And so what we really look at a lot in physics is the change in your position, or how far something actually traveled, or how far it actually moved. In big kid physics, you'll learn the difference between that word and the word displacement. As far as I'm concerned, in 9th grade physics, look, y'all, distance and displacement are the same thing. That's not true. That's why I have this little asterisk on here. It's actually not the same thing, but it's good enough for us. Take big kid physics someday, and I'll teach you the difference. But the big idea here is that our position is where you are, and distance traveled is how much your position has changed. Right, and so you might say something like, oh, this kid went from the 4 meter position up to the 9 meter position. In algebra, you might call this x1 and this is x2, and so our change in position then, our final minus initial, or x2 minus x1, is going to be a gain of 5 meters. So this kid went forward 5 meters because he went from 4 up to 9. Nothing too difficult yet. And our third vocab word for this unit is going to be speed, which, like I said earlier, I'm going to lie to you a little bit here. I told you that the distance traveled is the same as displacement. It's not. You'll learn the difference someday in big kid physics. Speed, I'm going to use interchangeably with velocity. That's not true. They are different, but it doesn't matter for us right now. And speed is how fast you are moving, or the rate of change, or how quickly you're changing your position. So something with a really big speed is gaining a lot of position or losing a lot of position really fast. Something with a small speed isn't moving that fast. People say physics is hard. See? That's easy. So now we got to move on to how to read a graph, but there's really 2 types of graphs that we're going to use in this unit. And the first one is just a plain old y versus x diagram, just like you guys did in Algebra 1, where you'd see, motion is doing this, or here's a graph of the object's position as a function of time, or maybe it looks something like that. The second one is a new type of graph you've probably never seen before called a dot diagram, and this one's actually a little bit easier for us to understand right off the bat, and so we're going to go with that one first. So in a dot diagram, what you're actually going to draw is a dot representing the position of the object that we care about at equal time intervals. And like there's old spy movies where they would hang a can of paint under someone's car with a small hole in it, and it would put these little dots of paint as the car drove down the road. You can just think about like as something is moving across my screen right here, every second I'm going to put a dot wherever it actually is. So we can tell a whole lot from these dot diagrams. We can tell whether it's moving or whether it's not. So let me pause this and erase real quick. So if the object is not moving, what you're going to see is the first dot and the second dot and the third dot and the fourth dot and the fifth dot and the sixth dot and the seventh dot. They all wind up going in the same place, and you're going to wind up having a really big pile of ink after a while. So we're not going to see any change at all in its position. Now, representing a object moving on a video like this is really easy for me to tell you that it's moving right, because all I have to do is come through here and you see that each next dot appears to the right of the... What's going on with my Apple Pencil right here? Weird. Each new dot appears to the right of wherever it was before, and so we can actually see that these are moving to the right. If you're not looking at a video, if you're looking at a picture, what we'll often do is show the history of all these dots and then have an arrow underneath of it or on top of it saying, hey, the object was moving this way, right? So moving left, it's going to be similar. If you're watching a video, you'll see each new dot appear to the left of the one before it, and so it's real obvious that the object is moving to the left. If you're looking at a still picture, we'll represent that it's moving left by showing that right there. Okay, so if you think about a car that's moving at a nice constant speed, maybe this thing is just cruising at 2 miles an hour, 4 meters per second, or whatever. In the first second that goes by, there's a dot, and a second later, there's another dot. And if it's going at the same speed, if the rate of its position is not changing, then in every second, it's going to cover the same amount of distance. Its position will be changing at a nice constant rate. And what we see on this is the dots are all going to be equally spaced apart, right? These two dots are the same distance apart as these two dots. They're the same distance as these two. And every second that goes by, the object is moving the exact same distance. And so we say it's moving at a nice constant speed. Now, if the object starts out going really slow and speeds up, it's not going to be nice and equally spaced out. What we're going to see is that each of these dots is going to change how far it is away from the next one. So maybe it starts here, and in the first second it didn't go very far, and so it's only that far apart. But in the next second it's going a little faster, so it covers a little bit more ground. And in the next second it's going a little bit faster, and then a little bit faster, and then a little bit faster. And what we see here, when you see the spacing getting bigger, right? This is an object moving to the right there. What we're going to see is the spaces increase if it's moving faster. And if it's moving to the right, if it's moving to the left, then of course what we're going to see is these little tiny gaps between each dot will get bigger and bigger and bigger in the leftward direction right there. So speeding up means you're gaining more ground every second, and the way we represent this on a dot diagram is that the dots would get further apart. Similarly, for a object that's slowing down right there, we're going to start out by seeing a big change in its position getting smaller with every second that goes by. And so these dots are going to get closer and closer and closer together. That's, of course, for something that was moving right. For an object that is moving left, slowing down would be big spaces getting smaller and smaller and smaller, looking something like that. Of course, you can also have combinations of these. This diagram right here of these red dots, assuming it's moving to the right, is showing big spaces getting smaller, and then having nice constant spacing in between, and then getting bigger and bigger and bigger. So over here, what we see is this thing is slowing down. This is going at the nice same speed, and then this one over here is going to be speeding up as it goes to the right. Alright, so those dot diagrams are really pretty easy if you just think about that each one of the dots is made at an equal interval in time. The question now is, what would this look like on a traditional graph of y versus x? So when I compare two dot diagrams here, both of them just moving to the right because, I don't know, I had to pick right or left. The one in black, the dots are spaced really close together. So in every second, this top guy here went here, and then a second later went there, and a second later went there, and a second later went there, and blah, 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 all the way to the end. The one in blue was covering more ground every second. So in each second, it went that far. And so what this looks like on a graph really ought not to be that surprising. When we graph stuff in physics, time is almost always the independent variable. So we're always going to put time down here on the bottom axis. And so if we think about as the time goes left to right, or as the time flows, we're going to be reading this graph from left to right like this to see how the object is actually changing. So if we look at this top one here, this guy right there, these black dots, let's just have them start here at the beginning. This is going to be our position, of course, on this axis. In each second that goes by, they're not gaining very much position. So every little tick of the clock that goes by, they're only going up a little bit because this distance from there to there isn't very much. You contrast that with these blue ones right here. And in each second that goes by, they've gained a whole lot more distance. So the little black one only went up about this high right there, but the blue one gained that much distance right there. And after the second, it's that high. And after the third one, it's this high, and the fourth one, this high. What we see is that these blue dots, because they're spaced further apart in distance, wind up giving us a much steeper looking graph right there than the black dots do. Right? The slow one down here has a smaller slope. It is a flatter graph. The faster one, the blue one, has a much steeper slope and it's a higher graph. If we go back to the very definition of speed, which is the rate of change of your position, well, that's algebra 1 right here, folks. The steepness or the slope of the graph is literally the rate of change of position over time. And so it should make sense that a faster moving object has further spaced dots and a steeper position versus time graph. Alright, so that was easy enough for us to do for graphs of things that are moving to the right, but things that are moving to the left might be a little bit tougher, except they're not. Here, again, we'll have a slow one moving like this, and every second that goes by, it doesn't cover very much distance, and we'll have our fast one that goes, let's just say, twice as fast, and so it's covering 2 meters or inches or whatever for every second. But the difference here is that these guys aren't moving positive. They're not gaining position. They're not getting bigger and bigger and bigger and bigger. They're getting smaller and smaller and smaller. And so a leftward motion or a, where is it? Negative speed. I have it on here somewhere. No, it's in there somewhere. A leftward motion or a negative speed is not an increase. It's going to be a decrease. So they're starting way out here, and they're working their way back to what we've defined as the origin. And so a slow leftward or a slow negative speed is going to be losing just a little bit of position every second. It starts with some bigger value, and it works its way backwards back to the start. The faster one, assuming that it's starting in the same position, is going to lose even more position than the other one. Now, you guys might be wondering what in the heck this means if it goes under the x-axis right there. It means nothing at all. This is arbitrarily defined as some starting point. You know, it's the start line of a race or something. If you go under the x-axis, all these down here, these negative positions, it just means you're behind the starting line. No big deal. But just like with things moving to the right, the steeper the line, the faster it's going. Right? So over here, this blue one is moving backwards really fast, so it's a big negative slope. It's moving fast. This one is much less of a negative slope, and so we say that this is the slow one. Alright, so a graph of an object who is changing its speed, a graph of the position of the time of an object whose speed is changing isn't going to look like these two. Right? These are straight lines because in each second, this slow object is covering the exact same amount of distance if it's moving at a constant speed. And this fast object is covering the same distance because it's moving at a constant speed. But if you were changing your speed, what that means is that each second that goes by, you are changing how much ground you cover. And so I'm going to do this red one first here. This is an object that, well, ask yourself, this object moving right, this dot, the red ones here, is this speeding up or slowing down? Hopefully you look at that and say, hey, well, as I read that from left and right, the distance gets bigger, so it's speeding up. So what happens with this guy, and I'm just going to start this at the origin here because why not, is that in the first second, right here, it doesn't go very far. And so maybe it only gains like, one little unit of position right there. Well, actually, I don't want to make it just one. Let me draw this a little bit differently. In the first part of the time that goes by, it doesn't gain very much. But then in the second interval of time, it gains a little bit more. And in the third interval of time, it gains even more than that. And in the fourth interval, it gains even more than that. So what happens is that instead of having a straight line, because every second that goes by, it changes by the same amount, if you're changing your speed, this graph is going to wind up being curved. All right? And when it gets faster, it should get steeper. There's a whole branch of math called calculus whose job it is to take a curve like this and to be able to calculate the exact slope of that point right there. We're not worried about that. What we're going to do in here qualitatively is say, hey, this is the less steep part, here's the medium steep part, and here's where it gets really, really steep. So up here, it must have been going really fast, which is true, because in that interval it covered more ground. Down here, it wasn't going very fast, and that's true because we can see that it didn't cover very much ground from that first tick to that second tick. Looking at the second guy on here. Look on the second guy over here. Moving right, moving forward, but it's slowing down. This is going to be kind of the opposite shape. So in the first second, from here to here, this thing covered a whole lot of territory. It moved a whole lot. And in the next interval of time, it didn't move as much. And so maybe it looks something like that. And in the third interval of time, it slows down even more, and it slows down even more, and slows down even more. And so what we're going to see is that unlike the red graph where it was getting steeper, this one is going to be slowing down. We see this green graph gaining less and less and less distance every time for each of the dots in time. One big important thing to note here is whether you are speeding up or slowing down or moving at like a constant speed like this, if the graph, as you read from left to right, goes up, these are all going to be instances of forward or positive motion, right? So the green one's moving forward and slowing down. The red one's moving forward and speeding up. The black one's moving forward at a constant rate. If we were going to look at objects that were moving backwards, well, we'll expect their graphs to look a little bit different. Right, so because they're going to be going backwards, these graphs are not going to be going up, whether it's curved that way, that way, that way, or that way. These graphs are moving backwards, and so they're not going to be gaining position. They're not going to be getting further and further and further away. They're going to be getting closer and closer and closer to the origin. So a backwards motion is always going to be some sort of downward trend, whether it's like that, whether it's like that, whether it's like that, whether it crosses the axis, whether it starts at the starting line and goes all the way backwards. If it's a negative trend, if it moves down and to the right, that means it's going backwards. So looking at our first one here, in the green, we're reading this from right to left. If it's moving to the left right there, we see in the first interval it doesn't go very far, and then it covers more, and then it covers more, and then it covers more. That tells us that this thing is speeding up. Speeding up, going backwards. So we're going to start up here at a high position, and we're going to draw a line, or a curve, that is moving this way. It's going downwards, but it's getting steeper as it goes. And so what that would look like is, at first, I didn't lose much position. I went just like a little bit forward, or a little bit backwards, and then I went a little bit more backwards, and then I got a little bit more backwards, and then I got a little bit more backwards, and we wound up with this trend where you were losing and losing and losing and losing more position every second that goes by. Contrast that with the one in the yellowish color here, where you started out going really fast and you slowed down. We're still going to experience a downward trend because it's still moving to the left or moving negatively or losing position or going backwards. But instead of getting steeper and steeper because it was going faster and faster, we're going to look at something that starts out really steep and flattens out. So this thing maybe starts, what the heck, let's have it start in the same position. The first second that goes by, it lost a ton of position. It went all the way down to there compared to that green one that only went like that far down right there. And then in the next second, maybe it doesn't lose as much. And in the third second, maybe it doesn't lose as much. And the fourth second, it's a little bit less. And so we're going to see a position versus time graph for something that's going backwards and slowing down as starting out steep, getting flatter and flatter and flatter and flatter like that. Okay. Big idea though, whether it's speeding up or slowing down or going at a constant speed, downward trend, trending downwards means going backwards. That's about it. So you guys are going to try and get the which one doesn't belong concept builder done, read the directions on the assignment, and hopefully that helps. If you guys have questions on this, just message me on Schoology.